Hello, this is the Section 7.4 lesson. For this lesson you will need to print table A3 from page 754 in your book, and you will also need the calculator. In this section we're going to talk about a concept that's very similar to what we saw in the last section, but instead of dealing with population proportions, we're going to deal with estimating population means. So suppose we want to know the mean IQ score of all statistics professors. We test the IQ of 25 statistics professors and obtain a sample mean of 121 and a sample standard deviation of 5.9. So remember here that X bar is an estimate of the population mean that I really want to know. So we have a point estimate of our population proportion, which is 121. Well, like in last section, whenever we estimate something, we want to get an idea of its accuracy. So how close is this sample mean to the true population mean mu? And we're going to answer it in the same basic way. We're first going to calculate a margin of error, and using that margin of error we're going to calculate a confidence interval. Okay. Now the one difference between this section and the previous section is that our critical values are not going to be z-scores. Critical values are going to come from a different type of distribution that's called the student t distribution. Student is a pseudonym for a guy named William Gossett, who did some of the pioneering work in statistics in the late 1800s and early 1900s, and he worked for Guinness Brewery, so he was brilliant. Sorry, that's my only statistics joke. Here on the right we see the density curve for the student t distribution. Notice that it looks somewhat similar to the standard normal bell curve. We have mean 0 right in the middle. However, one difference is that the student t distribution is a little bit different for each number of sample sizes. Now table A3, which you need for this section, gives critical values dealing with the student t distribution. It does not give areas underneath the density curve. If you look along the top, you see two column headings, area in one tail and area in two tails. Well, we're interested in the columns titled area in two tails, and that area in two tails is going to equal our significance level alpha. Along the left hand column you see degrees of freedom. Our degrees of freedom are going to be n, our sample size, minus 1. So here's our formula for calculating the margin of error for estimating a population mean mu. Let S be our sample standard deviation, which comes from our sample. N is our sample size. T sub alpha divided by 2 is our critical t value with n minus 1 degrees of freedom. Alpha is the area in two tails. And here's our formula. Margin of error is t sub alpha divided by 2 times s divided by the square root of n. Now one quick definition here. This quantity s divided by square root of n is called the standard error of the mean. Some articles, instead of giving the standard deviation of a sample, they will give the standard error of the mean, which is simply the standard deviation divided by square root of n. Now once we've calculated our margin of error, we can calculate our confidence interval for mu in the same basic way as before. We're going to take x bar minus e and x bar plus e, and mu is somewhere in between those two numbers. Now in interval notation it's there at the bottom, x bar minus e comma x bar plus e. Again, it's done very similar to what we saw in the previous section. So let's go back to this example. A sample of 25 statistics professors has a mean IQ of 121 with a standard deviation of 5.9. Let's find the confidence interval that corresponds to a 90% confidence level. Okay. So our first step is similar to the first step that we saw in that last example from last section. First we want to define the parameter. Now again, this is a step that I like to do. The book doesn't do it though. Here we simply state what it is we're trying to estimate. In this case it's mu because it's a population mean, and it's the mean IQ of all statistics professors. That's what I really want to know. We stress the word all there because we're interested in the mean of all statistics professors, not just the 25 in my sample. Okay. Now I need to calculate my margin of error, but in order to calculate margin of error I first need to know my critical value. So we're working at the 90% confidence level because that's what was given in the problem. So alpha is 0.1. n is equal to 25, so my degrees of freedom is 24. So I go to my table A3. I first go to the column area and 2 tails of 0.10. Next I go down to 24 degrees of freedom, and the corresponding value there is my critical value. So T sub alpha divided by 2 is 1.711. Okay. So there's all the numbers I need. My sample standard deviation of 5.9, n is 25, x bar is 121. Plug in my numbers, 1.71 times 5.9 divided by square root of 25. And there on the right hand side you see the calculator commands, and our margin of error is 2.0, rounded off to 1 decimal point. Next we want to find our confidence interval. Again, we're going to use this inequality notation. So x bar minus e, x bar plus e. So 121 minus 2, and then 121 plus 2. So mu is between 119 and 123. Now we would interpret this in the same way as what we did in the previous section. We would say we are 90% confident that the true value of mu is somewhere between 119 and 123. And again, the 90% confidence level means the same thing as in the previous section. This means that if we were to do a whole bunch of different samples, for each one of those construct the corresponding confidence interval, 90% of those confidence intervals would contain the true value of mu. Alright, let's look at another example of calculating confidence intervals. This we're going to use some data that we saw back in Chapter 2. Data set 2 in Appendix B includes 106 body temperatures for which the sample mean is 98.2 degrees Fahrenheit and the sample standard deviation is 0.62 Fahrenheit. Used in the sample statistics, construct a 99% confidence interval estimate of the mean body temperature of all healthy humans. What does this suggest about the use of 98.6 degrees Fahrenheit as the mean body temperature? In this example, we're going to see another example of inferential statistics where we're going to be using our confidence interval to make a conclusion or generalization about a population. Okay. So we're going to do this very much similar to the first example. First define the parameter. Mu is the mean body temperature of all healthy humans. Again, I'm trying to construct a confidence interval for mu, and this is how we define it. We stress the word all there, again, because we are interested in the mean body temperature of all healthy humans, the population of all healthy humans, not just the 106 in our sample. Next up is to find our critical value. First of all, we're working at a 99% confidence level, so alpha is 0.01. N is 106, so I have 105 degrees of freedom. So if I go to my table A3, and this is looking at kind of the bottom half, the first thing I note is I have to go to the first column because where area and 2 tails is 0.01. Next I go down to 105 degrees of freedom, but I don't have exactly 105 degrees of freedom. So I'm going to go to the value as close to it as possible, which is going to be 100. So the corresponding value there, 2.626, is my critical value. So now I use that critical value along with my sample standard deviation to calculate my margin of error. Okay. S is 0.62, that comes from our data. N is 106. So plug in our numbers. 2.626 times 0.62 divided by the square root of 106 comes out to be 0.158. Next we do our confidence interval. There's our formula: x bar minus e, x bar plus e. X bar is 98.2, E is 0.158, which we just calculated. We plug in the numbers, and there we get 98.04 is less than mu is less than 98.36. Okay. Now, we would interpret this confidence interval in the same way as what we did in last section in the first example. We would say we are 99% confident that the mean body temperature of all healthy humans is between 98.04 and 98.36. Well, first of all, note that 98.6 is outside of the confidence interval. 98.6 is quite a bit larger than our upper confidence level, confidence interval limit. So that means that the mean body temperature of all healthy humans is probably less than 98.6. It doesn't prove it. We never want to use the word prove when interpreting statistical results, but it is strong evidence that the mean body temperature is less than 98.6. Now, this formula for margin of error and confidence intervals are programmed into our calculator. The command is stat tests option 8 for t interval. This is called t interval because we're calculating a confidence interval and our critical value is a t-score. So there on the left figure you see the command option 8. If you press enter, you get a window that resembles this middle one. There at the top you see the name t interval. Next it asks for input, either data or statistics. If we have the raw data available, we can enter it into a list and then enter the name of that list, and it will calculate the mean and standard deviation for us and the confidence interval as well. But that's not what we have here. We have summary statistics. So we're going to choose that option stat, and then below that we need to enter the sample mean, and then Sx is the sample standard deviation, N is our sample size, and C level is the confidence level. So your window should resemble this one in the middle. You hit enter, highlight calculate and hit enter, and a result is shown there on the right. So t interval 98.04 up to 98.358. So mu is somewhere between those two numbers. Now those two numbers are maybe a little bit different than what we got using the formula, and that's because the calculator uses a more exact value of the critical value than what we used. Below that it also gives x bar, sx, and n. We can simply use those to confirm that we entered the numbers correctly into our calculator. Okay. Now the requirements to use this formula are two of them. First of all, the sample must be random. That's always going to be a requirement. And then second, either the sample is from a normally distributed population or n is greater than 30. Now these requirements are identical to the requirements for using the central limit theorem, and the reason is because the central limit theorem forms the theoretical background for this formula for margin of error. So that's it for this lesson. The Course Compass homework is titled Section 7.4.